Hi students, welcome to another video on control systems. In this video we'll see the modeling of mechanical systems. Before we start the topic, let us go through these few initial slides. To understand this topic, you should know what is Newton's third law, which states that every action will have a opposite and same reaction. Uh, Keeping this Newton's third law in mind, we will be modeling the given mechanical systems and then trying to obtain the transfer function of a given mechanical system. Okay, this is a few initial thoughts. Okay, fine. So let us move ahead with modeling the mechanical system. So let us uh, consider a mechanical system which is the simplest possible mechanical system you can consider. So there is a mass represented by m. So there is a spring represented by a constant k, and there is a friction between mass and the reference ground. Let us call it as b, and if this is the applied force in this particular direction. So this happens to be the applied force. Now we know that there is, for every acting force there will be opposing forces. So for this particular system having mass m, friction constant b, and spring constant k, if I'm supposed to write the equation, Newton's equation for this, so first of all we should write a free body diagram which indicates writing all acting and opposing forces on this particular mass. So this is mass. The acting force is over here, which is F. So because of this acting force in this direction will yield a displacement, a linear displacement or a translational displacement in the direction of the applied force, let it be x. Because of this displacement and because of this force, so there is an opposing force for this motion of m, which is given by mass into acceleration, which is nothing but double derivative of okay, this is d square x by dt square. So we have mass into acceleration, which is nothing but mass into d square x by dt square. So this is acceleration, which is nothing but double derivative of the displacement x, and we have another opposing force due to the friction, which is nothing but v into dx by dt. So it's actually due to friction, it is v into v, that is velocity, which is nothing but v into dx by dt. And due to this spring constant there is an opposition which is given by k into x. So the opposition due to the spring constant is k multiplied by the displacement of this particular spring. Since spring is connected to mass, by whatever distance this mass moves by a distance x, the spring will also, one end of the spring will also move by a distance x, because this is rigidly connected. So now these three are the opposing forces. So I can write this simply as v into x dot, where dot indicates a derivative of x. Now since it is double derivative of x, so I will write it as mx double dot, mx double dot. So now I can write force is given by mx double dot plus bx dot plus kx. So this is what is the acting force. These three are the opposing forces. If you take Laplace on both sides, so I will get f of s is equal to I know that this is m. Since it is a double derivative of x, this will become s square x of s, plus since it is derivative, it will become b into s into x of s, and since it is x, it will become x of s. So now what is the equation now reduced to? F of s is equal to ms square plus bs plus k whole multiplied by x of s. So this is the equation for this particular mechanical system. So we could able to write this is the equation by writing free body diagram. I will write it as this is free body diagram. Free body diagram. So this is a linear or translational motion. So let us consider another example where you have something like this. So let me consider an example where you have maybe we can consider. So now let me consider this as my second mass. So this is the representation of a friction which is represented by a dashpot. This is dashpot representing the friction. You can see this is a piston, this is the outer cylinder, and you can say this is, again let me say this as K1, this is B12, let me say it as M1, let me say it is M2. Let me consider there is no friction here, so let me consider as friction B2. Let me apply a force F here. Now this is your rigid surface. So because of this applied force, let us assume a displacement of x1 in the direction of the applied force. So let us consider one more displacement. This we have another displacement x2. So now before we start writing the equation, let us write a free body diagram. Free body diagram. So for writing free body diagram, let me separate the masses. This is m1, m2. Sorry, this is m1. This is m2. This is the acting force in this direction. This is F, and this is having a displacement x1. The opposing force is due to the mass itself, which is now m2 x1 double dot, and due to this friction B2, this is B2 x2 dot, sorry, this is x1, this is x1, and you have a dashpot connect between this and this, so this has a relative displacement of x1 minus x2. So now this is another force. So what is this magnitude? It is B12 x1 dot minus x2 dot. So these three are the opposing forces. Since this B12 is connected between M2 and M1, the one which is opposing the motion of M2 will want to actually act on M1. So this happens to the acting force. You can see the acting force is F in this direction. The acting force on M1 due to B12 is in the same direction as that of F. The magnitude of acting force of M1 is one of the opposing force for M2, which is this, which is connected between M1 and M2. And what are the opposing forces? Opposing forces are due to mass itself, which is M1 x2 double dot, and you have this is K1 x2, and you can see there is no friction here, so I don't have a friction exclusively for M1. So now we have written the free body diagram. So let me just summarize. The acting force on M1, M2 is F towards the right direction, and you can see the opposing force is due to M2 due to friction. You can say this is due to friction B2, and there is one more friction between M1 and M2. You can see this is B2 is having a displacement of x1, M2 is also having a displacement of x1, whereas B12 has got a displacement of x1 minus x2. That's a relative displacement. So using these two free body, okay, using this free body diagram, I can write the equation. equation is f of s, because let us take the Laplace directly. F of s is equal to m2 s square plus b2 s multiplied by x1 of s, that's what is this, plus of b12 s into x1 of s minus x2 of s. So this is the equation corresponding to this, and this happens to be the acting force, that is, this happens to be the acting force for m1. I can write this as my acting force b12 s into x1 of s minus x2 of s is equal to the opposing force, which is nothing but m1 s square plus k1 multiplied by x2 of s. So these are my equation for this particular system. We are just simply writing the acting force on one side and its Laplace on the right hand side. Again, this is my acting force on the left hand side, the opposing forces on the right hand side. So wherever it is double dot, I am writing it as s square, because it is double derivative of a Laplace is s square. Let us move ahead and then try to find out for one more circuit. So let us consider a system which is having something like this here. This is another. So let me consider. This is something like this. So let me apply a force F. Let this be the rigid body. Let me say this is K1, M1, K12, B12. Some naming here. I'm just giving this as B1. So there is a friction B1 here. There is an indication there is a friction B1. Now this is the force that is applied. So we know that since the force is applied here, so there is a displacement on this end of the spring, which is x1. On this end of the spring also, it will go by x2. The same displacement will happen here also. So the displacement what you have now is x1 and x2. Now whenever you have the force applied directly to this spring, so what you can think of doing is you can think of adding a dummy mass with m equal to 0. So now let me write the FBD. So this is my mass with m equal to 0. Let me start writing the acting and opposing forces. So what are the acting force? Acting force is this F. The opposing force on this mass is in the opposite direction, which is nothing but K1. What is the relative displacement of K1? It is x1 minus x2. So it is x1 minus x2. Since mass is 0, this doesn't have opposing force due to this mass itself. So now this force, this opposing force happens to be the acting force on M1. I'll write the same magnitude. Now it's on M1. So what are the opposing force? The opposing force is due to M1 itself, which is, now the displacement is, here the displacement is x1, here the displacement is x2. So what is this now? M1 x2 double dot, and due to this B1 and B12, both of them are having only x2 displacement. It is now x2 dot, and how about this K12? It is K12 x2. K12 x2. Now since it is rigidly connected, this B12 as well as B1 will have a displacement of x2 only, and its velocity is x2 dot. So can I now write f of s is equal to k1 x1 of s minus x2 of s. So now this is my acting force, opposing force is this. Now this happens to be the acting force, that is k1 x1 of s minus x2 of s is equal to, what is, that's what is, this is the acting force, which is this, which is that is written here. The opposing forces are M1 A square plus B1 plus B12 S plus K12 into X2 of S into X2 of S. So these are my two equations which are modeling this particular system. Okay, this is about another thing. Let me try to write for a rotational system. So let me consider a rotational system which is something like this. So let me consider a rotational system which is having some spring constant and some inertia which I'll represent it as J. And let me consider that is something like this. And you have this again, and assume that this is the torque that is applied. So let us assume that this is J1, K12, B12, and assume that this is K2. Now, because of this applied force, so there will be displacement in the same direction of the applied torque, that is theta 1, and this will have a displacement of theta 2. Let this be J2. Now let us again write the free body diagram for this. So you have a inertia G1, the acting torque is in clockwise direction T, the opposing torques are due to the inertia itself, which is nothing but J1 theta 1 double dot, and of course you can see it's in the opposite rotation, opposite direction. This is now B12 theta 1 dot, and this is in the same opposing direction, which is K12 theta 1. So now these two will happen to be the acting torque on this J2. Acting torque on J2 is in this direction. You can see it is in the same direction as that of the original torque applied. So what is its magnitude? It is B12 theta 1. This B12 has a relative displacement between theta 1 and theta 2. So it is theta 1 dot minus theta 2 dot, and this is theta 1 minus theta 2. This is the torque which is acting on J2. This is the torque which is acting on again J2. What are the opposing force? Opposing force is due to J2 itself, which is now J2 theta 2 double dot, and another opposing force is K2 theta. So now if you start writing the equation, you can write T of S, that is torque is nothing but J1 S square plus B. Okay, this is theta 1 of S, theta 1 of S plus B12 theta 1 of, okay, B12 S plus K12 whole multiplied by theta 1 of S minus theta 2 of S. Now your equation, let me rewrite this. T of S is nothing but J1 S square theta 1 of S plus you have B12S plus K12 having same displacement, which is theta 1 of S minus theta 2 of S. Now this entire thing happens to be the acting force. So I can write B12S plus K12 into theta 1 of S minus theta 2 of S is equal to the opposing force, which is nothing but J2 S square plus K2 multiplied by theta 2 of S. So these are my two modeling equations for this rotary system. This for rotational motion. So because of this applied torque, you have an angular displacement of theta 1, angular displacement of theta 2. So the overall modeling will look like this. Now we will see few more such things. Let me write more such system having something like this. So let me now take uh, a spring constant. Let me take inertia J1. Let me take another inertia J2 here, and let me consider a spring constant. Let this be this, and let me have a friction here as B1. Let me have friction here as B2, and let me have a friction here as B3. So now this is the direction of applied torque. This is my reference. This is, let us assume this is K1, this is K2. Okay, because of this applied torque at this end of the spring, let us assume that there is a theta 1. Here also it will have theta 2, and this will have another angle theta 3. This is fixed. This is fixed. So we will not have three angular displacements due to the applied torque for this particular system. So can I now directly write, since this torque is directly applied to this, you can consider a dummy uh, j equal to 0. I can consider this j equal to 0 here. There is no applied torque. The opposing torque is due to this k1, which is nothing but k1 theta 1 minus theta 2. This happens to be the acting force on J1. This happens to be the acting force on J1. So what are the opposing forces? Opposing forces, one is due to exclusive J1, that is J1 theta 1 double dot, and other one is due to, maybe let me write the other one is due to B1 theta 1. Okay, sorry, it's not theta 1, it's actually theta 2. Theta 2 dot, this is again theta 2 dot here, and you have this friction between J1 and J2. So this is again in the direction of the opposite torque. It is now B3 theta 2 dot minus theta 3 dot. There is a opposition over here, this B3. This happens to be the acting torque for this J2. You can see this is the acting torque on this. It is now J2. The opposing torque is due to J2 itself, J2 theta 3 double dot, and there is one more opposing torque due to K2 theta 3, and there is another opposing force due to B2, that is B2 theta 3 dot, theta 3 dot. So here for this we have 1, 2, 3 opposing forces. For this also we have 1, 2, 3 opposing forces. If you write the equation for this, then this becomes TFS is equal to K1, that is K1 theta 1 of S minus theta 2 of S. That's what it is. Acting force is equal to, acting torque is nothing but TFS. The opposing torque is this. The same opposing torque will become the acting torque for second inertia, that is K1. It is now K1, sorry, J1 theta 1 of S minus theta 2 of S is equal to J1 theta 2 double dot plus, okay, let me write, because I am writing in terms of it is J1 square plus B1S, correct, is the thing, which is nothing but theta 2 of S plus, due to this B3, it is B3S theta 2 of S minus theta 3 of S. This happened with acting force, which is nothing but B3S theta 2 of S minus theta 3 of S is equal to the opposing force. One is due to J2S square plus B2S plus K2 theta 3Fs. Theta 3Fs. So these are the equations governing this particular system having these many inertia, spin constant, and frictions. You're simply writing the left hand side the acting torque and on the right hand side the opposing torques. So this way we can able to comfortably write equations for a given mechanical system, which will tell us what is the displacement, relative displacement, and their acting torque or the opposing torque or acting force or the opposing forces. So with this knowledge, we shall proceed towards modeling of electric motors, especially DC motors, and try to understand how to find the transfer function of a DC motor. Thank you.